So hello, good afternoon, everyone. It's a great pleasure to have all of you here. Thanks a lot for joining us in this workshop by mQACC. We are really excited to be here and to have all of you here. So that's our real pleasure. For the workshop today, we have a couple of major goals we would like to accomplish. We will very briefly introduce what is mQACC, what we do, why we feel so excited about it, and about being a part of this organization. And we will also share with you some of the best QC and reporting practices in metabolomics we are currently working on. So for the next 2 hours, a bunch of people from mQACC, we are going to be sharing those ideas with you, and I would like to introduce each one of them. So you can maybe, guys, stand up as I say your name. So, well, my name is Victor Gonzalez. I will be the moderator today, and I will start talking about the introduction in this workshop today. But we also have, I'm coming from CEU San Pablo University in Madrid, Spain. With us, we have Dajana Vuckovic, who's coming from Concordia University in Canada, sorry. Oh, this CA was a little bit misleading. My apologies. But I'm fully aware that's maybe they have a better weather down there, yeah. And Jennifer Kirwan, who's coming from Austria. Leo Cheng, where is Leo? There, coming from the USA. Mariana Santos from London, UK. And then Kuligowski from Valencia, Spain. So for those next 2 hours, the idea is that for the sake of timing, we are going to try to go just straight. And we have already planned to have half an hour for questions and discussions at the end. So that would be maybe great except if you have any burning questions, you can maybe hold them till the end, and you can share them with the whole audience, and we can discuss about them by the end of the workshop. On top of that, we are going to run a walk lab poll in some 10 minutes or so. So get ready your mobile phones, your cell phones, so you can snap the code and join the poll. Okay? So let's start with a very brief introduction to mQACC and QA and QC and what we are doing as a consortium. So you're probably familiar with some of those ideas of quality management, quality assurance, quality control, but maybe all of them sound quite similar to each other. So under this umbrella of quality management, we have a number of different concepts. So what we are going to cover today is quality assurance and quality control. Quality assurance refers to everything we do in advance. So how we get ready, how we prepare our lab, our analysis, our sequences, our people, our staff, how we get everything ready to get the best results from our analysis. And then quality control are all of those activities, all of those checkpoints we put in place just to make sure the quality of our analysis was the one we were expecting, and to evaluate it and to eventually correct any issues when possible. And then there are other activities, such as risk management or the continual improvement, but we are not going to cover them today. So again, just to insist on that idea, it's everything about timing. So quality assurance are those measures, all of those activities we perform just to get everything ready, and everything we do before acquiring our data, just before going into our analyzing our actual samples. Not only the dry lab and everything we can prepare in advance, but also some of the samples, some of the activities we already perform in the lab are dealing with quality assurance. And then quality control, and we are going to extensively cover them today, are all of the activities related to evaluating this quality, detecting any issues, and potentially, when possible, fixing them. So those are the two major fields of activity for mQACC. So where does mQACC come from? mQACC was founded almost 10 years ago following a think tank which took place in the National Cancer Institute in October 2017. So it's already almost 10 years old. The mission is to engage, to disseminate, to get to know, and to also to facilitate the community, the adoption of the best practices and the good practices in quality assurance and quality control in metabolomics, and to harmonize all of them. We are currently almost 240 members from all around the world, and also coming from academia, industry, and governmental institutions. So we are trying to have a very large and varied representation of everyone doing metabolomics, because again, the point is to get to know what are the currently best practices and good practices, and to disseminate them to the whole communities, to make easier for everyone to adopt them and to put them into practice. We have a coordinating committee, and we have some secretary, which are really very supportive and always helping a lot. And then the organization is divided into a number of working groups. So each working group is taking care of some particular tasks, and we are specifically dedicated to working on those tasks in smaller groups. So we have regular meetings for the whole mQACC community, and then we have usually more regular, those meetings in the smaller work groups are usually more, we are having them more often. And across all of those work groups, working groups, we try to answer questions like, what is the best practice, or which is a common practice in the community? What do we need to report? How can we improve practices, or how can we adapt current practices to new technologies? So the idea is to establish the standards nowadays, the best practices nowadays, and the direction to go in the future. And as a result of all of this work, there are a number of outputs which have been done and published over the past years. We've been very actively organizing workshops like this one today. We have also brought many oral and poster presentations to different conferences. And there are a number of publications which have been also written and published by members of mQACC coming from those different working groups. So these are just a few of them. You can scan the QR codes, or if you would like to have all of them together, you can just go to our outputs web page, and there you'll find them along with other materials, such as, for instance, the living guidance and infographics, or our living guidance, which we hopefully we will be publishing very, very soon and making it available to the whole community. So very briefly, and to clarify maybe a couple more terms before we get into all of the presentations. So first of all, why do we need quality control in untargeted metabolomics? You are probably very familiar to targeted analysis and classical bioanalytical validation, in which we are targeting a few analytes, and we can fully validate the analytical methods for those particular analytes. But it is not possible to work like that when we are dealing with untargeted analysis, and when we are trying to broaden our coverage and to analyze hundreds or thousands of metabolites at the same time. So it is in this scenario that we really need some means to evaluate the quality of the signals we are acquiring and to eventually discard them or correct them. So in order to do that, there are a number of samples we use, and all of my colleagues are going to talk about them in the following presentations. We have system suitability test samples. Those we use as a part of the quality assurance to make sure that the analytical platform is performing as expected. We have blanks allowing us to detect any contaminations which are present in our samples or coming from our sample preparation or from the instrument. We are also extensively using standard reference materials, especially because they make easier to compare results across labs, and we are using a lot pooled QC samples, and again, my colleagues are going to talk about them. And those pooled QC samples, they are a pivotal element in QC, in metabolomics, in untargeted metabolomics, and they are used for different purposes. They are used to evaluate the instrument stability. They are going to use to evaluate the quality of the different features and eventually filter them out to correct those drift. They serve to many different purposes, detection of analytical outliers, and my colleagues are going to give you a bunch of examples about them in the following presentations. So that's it's about this very short introduction, and now we would like to go for a poll, and just to get to know you a little bit better. So let me switch to, OK, there we go. So please snap this QR code to join the poll. And then you should get into the system. Is it working for everyone? Yeah? Do you need maybe one more minute? Feel free to do it. Otherwise, you can just head to woclab.com and then type down this event code. It should work as well.
The Wi-Fi is quite slow.
Oh, OK. So we'll give a few more moments for everyone to get to the website. OK. Is everyone in? Can we move on? So let's get started then. So the first question is a very easy one. What's your experience in untargeted metabolomics? For how many years have you been practicing untargeted metabolomics? Less than, well, maybe you don't have any experience at all. Maybe you come from a different field, or maybe you have under 2 years of experience, 2 to 5, 5 to 10, 10 to 20, or over 20 years for the most experienced ones, or 20 years of experience. I should say I fall, well, maybe not that old. I'd fall in the 10 to 20 years. So. OK. So everyone voted. Can we check the results? So it looks like, well, we have 7 people not having any experience, and in total 15 people having under 2 years of experience. So that's maybe one of the driving forces of having this sort of workshops, because we try to introduce QA and QC to people which is coming new and fresh to the field, and then we have quite a bunch of people already having some experience between 2 and 10 years, and then 11 more people with over 10 years of experience. So that's really cool. OK, so I guess we can move to the next question. What technologies do you use when doing untargeted metabolomics? And here you can check as many of them as you use. So you can go for LC, GC, CE. For those weirdos doing CEMS, I am one of those ones doing CEMS. GC, and so on. So let's see how it is shared. I take the risk LCMS is probably the most popular one. Let's see. Not a bad bet, yeah. So everyone voted. Can we unveil the results? Exciting. Let's see. Oops, sorry. Wrong icon. There we go. OK, so yeah, not so surprisingly, LCMS is used by 93% of people voting, followed by GCMS, NMR, and well, there's one vote for CEMS missing there. This is my vote as well. And someone else is doing something else. Can I please ask who is? Spatial imaging. OK, great, great. Oh, someone else is also doing something else. So who's the second one doing other stuff? Can you please share with us? Don't be shy, come on. It's maybe imaging as well. Well, we'll assume it's also imaging. Okay, great. Thank you so much. So let's move on to the next one. So what type of QA practices do you use? And here again, you can apply, you can select as many as apply. Oops, sorry. So maybe system suitability testing, SOPs, standard operation procedures. Do you keep records of the different processes, like logbooks, training records, like all of the documentation? Maybe also you keep records of proficiency or competency testing you're performing to your staff. Maybe some data management policies, fair access, sharing, access restrictions or control, maybe long-term monitoring of the performance of your analytical platforms. Okay, so are we ready? Yes. So let's see what we got. Up. There, okay. So I'd say that, yeah, documenting processes is with a 75% is the most common, 76% is the most common practice when it comes to what's adopted or done by our participants, followed very closely by standard operating procedures. So it looks like everyone is trying to generate those standard operating procedures before everyone gets into running the analysis, and then some system suitability testing as well, and then maybe long-term monitoring, data management, and proficiency and competence testing are not so popular. Okay, so let's move to the next one. And here, if you're already familiar with those QC samples, so which sort of QC samples do you use in your analysis, in your daily routine? Maybe you use blanks, use internal standards, reference materials, maybe long-term reference materials. And again, you can check as many. Oh, it's not working? No? Yeah, it can be faster if you use just your cell connection. Yeah. Okay, so everyone got it? Let's have a look at the responses. Wow, so pooled QCs are very popular, and also blanks and internal standards. So, and then standard reference materials are not so popular. We are going to discuss them in detail as well, maybe because of price, access, let's see. And then long-term reference materials are also just 10 people are using them, and no one is using other stuff. Okay, so now let's move to the last one. So what is the major challenge you're facing in QA/QC for untargeted metabolomics? And here that's an open answer, so you can actually type wherever you feel into, and then we can also use those responses as a starting point for the discussion by the end of the workshop. Okay, so please go for it. Type them down. Is it maybe about training, about instrumentation, record tracking? Let's see. And I think that for the sake of time, we're going to reveal. Okay. Well, so we have quite a large variety of responses, reporting, SOPs, cost, training, lots of extra words. Wow. Metabolite ID, if you want seems to be repeating. Okay, well, so I'm pretty sure it's going to make a very good starting point to our discussion by the end of the workshop. Okay, so with that, let's move on. Thank you so much to everyone for participating. And with that, now we are going to move on to the next presenter, who is Dajana Vuckovic. Unfortunately, not from California, but from great Canada. And she's going to cover LC-MS QA, QC practices and case studies. So please, let's welcome Dajana.
So thank you, Victor, for introducing me, and thank you all for being here. So today I want to talk about a little bit about QC practices and show you examples either from literature or some of our labs, how we implemented some of these main practices that we recommend. So if you think about different sources of variation in LC-MS metabolomics, they can come from different parts of the workflow. During sample collection, we can have pre-analytical factors that are contributing to the variation that we are seeing. During the experiment itself, both from sample preparation side of things and from LC-MS analysis of things, we can introduce variability. And then during data processing stages, we can also introduce errors. For today's talk, for the sake of time, we are going to really focus only on that experimental variability. How do we control and evaluate variability that's coming from sample preparation and data acquisition stages, and we're not going to talk about pre-analytical and data analysis variability. And just to remind you of the goal of these QC strategies that we are trying to implement is really we want to control our technical variability, and we want to make sure that it's lower than the biological variability of what we are trying to measure. So this is really the key concept that we have to keep in mind when we are trying to think which QC strategies to implement and how best to do it for our particular study and for our particular question. So in terms of today's presentation, I've divided it in kind of 5 very short topics. So first, we are going to talk about how to design an analytical batch. So before you ever set foot in the lab to run your study, what kind of things you need to think about in terms of designing that batch. Then we'll talk a little bit about system suitability testing, how to decide whether to proceed with running your batch or not. Then during the analysis itself, hopefully you'll be using pooled QC and internal standards, and we saw from polls the vast majority, 80–90% of people were doing this, so that's great to see. So this is going to be controlling that experimental variability during sample prep and LC-MS stages. And then we'll end off talking about data quality review and deciding how to accept or reject a batch, maybe identifying some sample outliers, things like that. So to start with, first we can define what is an analytical batch. So this is a collection of experimental and QC samples from a study that are processed at one time and analyzed continuously. So if we stop the instrument to clean the source, that's not going to be part of the same batch. That's the main idea when we use this word, batch. And when we're trying to design these batches, there's different things we need to think about. So the first and maybe major question is, what's the total number of samples we can run confidently in a batch and ensure good data quality? And the answer to this question is going to be both method and instrument dependent, and maybe you need to do some experiments during the development to establish what's a reasonable number of samples using objective acceptance criteria. The next question you need to decide on is the layout of the batch, and the things to keep in mind there, you want to avoid bias, so you want to randomize your samples, and you want to have enough of these QC samples to be able to monitor that technical variability and be able to distinguish it from your biological variability. So these samples have to be frequent enough to allow you to do that. And then if you're doing more larger scale studies that cannot be run in a single batch batch that exceed your maximum number of samples for a batch, then you need to start to think about incorporating additional QC practices, for example, using long-term QCs or SRMs to ensure you have enough of different types of QC samples to collect and merge all of that data together in a high-quality way. So when we are talking about determining a reasonable size of the batch, the limiting factors can come from different parts of our workflow. We can have limiting factors that stem from sample preparation side of things. So if you are running very dirty samples, our batch sizes might be smaller because we need to shut down and clean the instrument because our sensitivity is dropping over time. Another limiting factor could be the instrumentation that we are using to prepare our samples. If we are using 96 well plate robotics, right, then we might be confined to that. If we are using centrifuges, speed wax, and so forth, we might be confined to how many samples can fit within the instrumentation that we have. Another often, I would say, overlooked part is how stable are these extracts after we've prepared them. If we know our extracts are only stable 48 hours at autosampler temperature, well, there is your batch limit, right? You cannot go past 48 hours. So those are some of the things to think about from your sample preparation side of things. If your extracts are stable, you can prepare hundreds of them in your lab, you're well set up on that, then maybe the limiting factors become LC-MS kind of things. Maybe your mass accuracy starts to drift, your signal starts to drift, and so forth. So then maybe you need to evaluate there what's a reasonable amount of time before these kind of things happen. So in terms of if you need a practical approach to evaluate, right, you could set objective criteria after which if the signal drifts more than that, for example, if the signal drifts more than 20%, that's when I should stop, do some corrective actions before I running a new batch, so that could help you determine your batch size. So let's look then at some example sequences. So as a first example, I thought I'd show a single batch sequence with blocking. So for this study, let's say we had 3 groups of samples. So group 1, group 2, and group 3. Maybe group 1, let's say, is healthy patients. Group 2 is the disease that we are interested in. And group 3 is a related disease, but we want to make sure that we distinguish group 2 and group 3 samples, whether we can distinguish them with the biomarkers we pull out. So a simple batch there might look like something like I'm showing there. So we start off first with our blanks and different types of blanks, and I'll show you a little bit why we run different types of blanks in a slide or two. Then we run our system suitability samples, and this helps us decide, do we proceed or not with the batch. Then you can say we have conditioning QC injections to get our system stable, ready to run our study. And then we start with, for example, 3 pooled QC injections. And we also end with 3 pooled QC injections, and we re-inject this pooled QC periodically throughout sequence. Most labs are somewhere between 5 to 10, 5 to 15 injections. Again, the frequency you have to decide yourself. And then in each sample block between the adjacent pooled QCs, right, you randomize your samples, and it's also good practice to block them as well. So that way you don't have batches, like blocks of samples where you only run samples from like group 1 or only from group 3. So if there is systematic drift throughout sequence, either a signal going up, down, or other issues happening, right, all the samples will be affected kind of in an equal way if everything is randomized and blocked correctly, so you won't interpret those effects as something biologically relevant. So in terms of these key ideas of building the batch, definitely SST is this point of go or no go with a further analysis. And the other thing I'll mention here, we recommend running blanks at beginning and end. At beginning to evaluate contamination, at the end to evaluate carryover, and we recommend avoiding running throughout because it may decondition your system. So if you are running blanks throughout, then during method development, you need to check for system deconditioning and whether you need to do some reconditioning injections to ensure your signal is not affected by running of those blanks. And then final point I'll make here is for your pooled QC samples, the frequency of injection has to be high enough to be able to do some statistics that are reasonable, right? So if you just have one pooled QC at beginning, one at end, this is not really going to tell you anything about drift or RSD or things like that. So you have to run enough that you can do some reasonable statistics. So then if we go to a little bit more complicated design, let's say we need to run similar 3 groups, but now it's a much larger study, it has to be spread across multiple batches. The sequence design can stay very similar, but what you can see here now, I've added this long-term QC, or it could be an SRM material as well, that's run periodically throughout a batch, so beginning, middle, and end. So this gives you an independent sample to evaluate once you start integrating your batches, if you have to do batch correction, things like that, using your pooled QC. It gives you another second independent sample that will allow you to evaluate whether correction is working well or not. The other thing to keep in mind with these batches, multi-batch studies, is you need to have enough of this both long-term QC material and your pooled QC for all the batches that you plan to run. So you really need to plan ahead and prepare enough to have for everything that's going to come after, right? And have some spare in case, you know, something goes wrong with a batch or two. So those are the main points, kind of what gets tricky with these more multi-batch studies. And then in terms of the blanks, you saw in my design of sequence, I was suggesting 3 different types of blanks at a minimum. So solvent blank will tell us what's present in extraction solvent, and it can be a good blank to use also to evaluate carryover. Process blank is a blank that you take throughout the entire procedure. So all the sample preparation step, it goes through all the vials, glassware, pipette tips, everything you're using, right? So it's going to have signals from everything along the path that might be relevant for the sample. And then system blank is a good check to see what's coming from your LC components only, so your LC system and mobile phase. So this is also known as no injection blank, because then it can help you troubleshoot. If you do have contamination that's unusual, having these types of blanks can help you tell where this contamination is occurring, and then you can figure out how to resolve it prior to your study. So then as the next part of our quality control process, we would set up a system suitability testing. So this is defined as analysis before the batch to check that our analytical system is working well. And here we can have 2 types of approaches. We can have what's called universal system suitability. So this would be system suitability that you do regardless of which method you're going to run. So let's say I have Helic and lipidomics and reverse phase method in my run. If I'm doing universal system suitability, it will be same across all of these methods. Or I can have assay-specific system suitability that also tests something specific to the method that I'm running. So for universal system suitability, usually this includes things like mass calibration, checking pump pressure, that gradients are working well, checking for contaminants, checking instrument sensitivity, and we are comparing the data against long-term longitudinal data. And the answer that the universal system suitability gives us is the system performing well. Is everything good with my system? That may or may not be enough, right? There might be assay-specific problems that you would encounter. So if you only run universal, you might miss out some potential problems. So for example, if your column is not working well, maybe you lost resolution of some of your critical pairs, right? So for that, you might want to have an assay-specific system suitability where you check retention time of selected metabolites, you check resolution of your critical pairs. If you're using derivatization, you check that the derivatization is working properly on that day, and so forth. So then this assay-specific SST tells you that the assay itself is performing well. So the way I think of designing this system suitability testing is kind of, it has to have these 3 components. One is like a simple mass calibration tuning, and most vendors have done a great job job of it for us, right? There is a vendor-specific solution. We run it. It creates automatic report. We can compare it against historical data so that makes sure everything on the MS side of things is working well. Then for the second and third part, you need to incorporate appropriate blanks to check for contamination. And I'll say here we sometimes have issues with even LCMS-grade solvents, and mobile phases may be contaminated, so it's worth checking that before starting your study. And then for the assay-specific performance of the system, you might have either a standard mixture of analytes that are relevant to that method. You might have a biological sample you want to run and check how the coverage is and how it performs there, or you might have both. And in terms of standard mixtures, typically most labs are using 6 to 10 standards. These should span polarity, retention time range, M/Z range, so you want to cover a broad range of compounds. If possible, it's nice if they ionize in both positive and negative mode, if you want to have a single standard suitability mixture, or you can have separate SST mixtures for positive and negative mode. Since you're going to be running this a lot, right, you want it to be inexpensive, so you try to pick compounds that are reasonably available. So for example, for this Helic method in positive mode, you can see here they're using 7 compounds for their system suitability mix. It includes fatty acid, amino acid, acyl carnitines. We have a critical pair of leucine and isoleucine to tell us that chromatographic separation is working well. And you can see example accepted criteria can look something like this. Maybe your M/Z error has to be less than 5 ppm, or if you're doing internal calibration, maybe less than 2 ppm. Retention time less than 2% compared to the defined retention time. Peak area might have acceptance criteria plus minus 10%, or whatever you decided. Symmetrical peak shape, you could use something like tailing factor less than 1.5 to ensure that the column is working well, and so forth. So then going back to our sequence, as we said, normally you would run blanks and these SST samples at the very beginning. And based on the results, you would either proceed to running the batch or you would stop and perform appropriate corrective action. Let's say if your chromatographic resolution fails, maybe your column is aging and you need a new column. So then you would change that and then rerun your system suitability before running your study samples. Some labs also perform SST check at the very end of your sequence to make sure everything is still working well once you finished your samples. This is optional. You can use other samples for the same kind of purpose, so that part is up to you, but we definitely recommend it for sure at the beginning of the run. And just to show you kind of what community uses, majority is using both standard and a biological sample as part of the system suitability, and then smaller number of labs are just using biological sample for system suitability testing. Then, so we've run our system suitability, everything is working okay, we can go ahead and run our study. So the next component we want to monitor is our technical variability throughout the run, and here we are going to use our pooled QC samples, and I was happy with the poll results. Looks like most of the audience is already using it, so this is great to see. And just a couple of definitions, just to make sure we are all on the same page there. So with our pooled QC, this is our matrix match sample where we take aliquots of our study samples and combine them together and run them throughout the sequence. System conditioning QC can be exactly the same if we have enough material, but I saw in some of those answers, sometimes people were saying there's not enough material and things like that. So if that's the case, it can be another bulk matrix of the same kind that you just use to condition your system. And for long-term QC, it's a bulk material available in large quantities that you can run over time, over studies, across labs, and so forth, to see how things are working. So when you are preparing these pooled QC samples, you have 3 main choices in terms of how how and when to do the pooling. So on the left-hand side, you can see we take all of our study samples, we prepare them, whatever the extraction method and everything is, and then just prior to LCMS analysis, you pool equal volume aliquots from all the samples. In the second scenario, you take your study samples, you pool them prior to extraction, and then you extract that sample same as you would for your study samples, and then do repeated injections on LCMS that way. And then the third case scenario on the right-hand side is you pool your study samples into pooled QC, then you take independent aliquots of that, and each aliquot is taken through independent extraction procedure and then analyzed independently on LCMS. So the difference there, right, is the two scenarios on the left-hand side are going to monitor just instrumental variability and not sample prep. And if you do on the right-hand side, then it's going to also tell you how good your sample prep is and how much variability is coming from that stage of the process. So then just to show you, in addition to monitoring technical variability, pooled QCs can have other important uses. So in this particular example, where I'm showing an example 96 well plate layout for a batch, you can see my pooled QC in green. Those are the technical ones that we are using to monitor variability. So I think most of us are using those ones. But then you can have other ones. The blue ones are the system conditioning injections that are very important to get stable signal. But then you can also get more fancy. You can start to monitor your linearity and matrix effects by using a dilution series of QC. So those ones are shown in orange on my sequence. And then you can also use pool QC to help your annotation, so to collect MSMS spectra, evaluate CCS values and other things. And those ones, for example, are shown in purple. So when you are designing your QC strategy, you also have to decide, right, what am I going to use my pooled QCs for, and make sure you have enough of injections for these different purposes that they may be useful. So then just to show you an example of evaluating pooled QC performance from this paper, you can have a look in more detail at the paper if you're interested. So this was a large-scale study with a couple of hundred samples. You can see they had pooled QC that's shown in blue, and they were also running NIST SRM 1950 material that's shown in orange. And you can see the initial processing of the data. You can see the drift of the pooled QC and NIST SRM. And similarly, if you look at your internal standards, there looks to be a time-dependent drift with signal getting smaller along the way. After correcting for this signal drift, you can see on the bottom, and also filtering the data based on quality, you can see now on the bottom, both the SRM and pooled QC are now clustering very tightly, and internal signal has been corrected appropriately. So now it's okay to go ahead and proceed with biological interpretation of that data. The other example I'll show you from this paper is showing you the difference in CV distribution for technical versus process replicates, because then it's going to tell you, depending on which of three scenarios you're using to prepare your pooled QC, your acceptance criteria will be different, whether you're only monitoring instrumental variability versus instrumental process sample prep variability. As you can see, of course, when we add sample prep, the variability is going to be higher as expected. And the other thing that I'm going to mention is definitely it's good to have objective metrics, so things like Euclidean distance, looking at D ratios, so comparing technical versus biological variability for each metabolite that you're interested in, and deciding on a cutoff when it's okay to use this data for that metabolite and when the variability may not be acceptable. So pooled QC samples help to tell us is there LCMS drift and things like that, but they are not injected, right? We are periodically injecting them every 8, 10, 5 injections, right? But how do we know if the injections in between are working okay when we are running our study samples? So this is why it's nice to have internal standards, and I like the poll results. It's at 80% of people are doing that, so that's amazing. In terms of criteria, it's very similar criteria criteria for system suitability. You want to cover polarity, classes, M/Z range. And in terms of numbers, people are running somewhere, I don't know, between 1 to 10. And our working group, literature survey working group, has done a systematic review on this topic. So the paper should be coming out before next Metabolomics conference. So keep an eye out on that if you are interested. And of course, the key requirement for your internal standards is it must not be present in your sample, and you must confirm that, right? Without that, things are going to fall apart very quickly. So just an example of a mixture. So this is a 7-component internal standard mixture for a short 10-minute method. Again, you see we are spanning chromatographic space, M/Z range, and so forth. And we can use it to evaluate chromatographic performance, MS and MS performance, and have appropriate acceptance criteria to decide whether everything went okay or not. So in this example, we are looking at peak area across samples and across QCs. You might have a different acceptance criteria for the two. And also RSD of the retention time in this case was 0.3%, and the acceptance criteria was 2. And in terms of internal standards, we can use them for 2 different purposes. If we spike them pre-extraction, then we are monitoring extraction recovery and instrumental variability. And if we spike them post-extraction, then we are only monitoring instrumental variability. And you might decide to have 2 sets where you do both, depending on what you are doing. So just to show you an example of what kind of information you can get if you use both sets. So this is an example where we spiked PC17 post-extraction. You can see a really nice stable signal telling us there is no major matrix effect, there is no LCMS drift, and so forth. For the CE that spiked pre-extraction, you can see now we start to see very interesting effects. It looks like the recovery is higher in the highly lipemic samples versus our control patient samples, right? So this recovery was not stable across everything within the cohort. So this can be very helpful when designing. And then when you see outliers across all of your internal standards, like sample 28 in this example, this can tell you about preparation error. So in this case, the internal standard was accidentally spiked twice. So then you can treat that as a sample outlier. And then for the final topic, so you've run your pooled QC internal standards, you've done system suitability and everything. So for the final data quality review, you can do some real time while the samples are running to check, is there anything you need to do? Maybe do you need to stop the run, or everything is working well? Or you, of course, you should do post-acquisition data review where you treat all of your data and decide to accept or reject a batch. So if you're doing real-time data review, usually it's using internal standards or selected metabolites. And the idea is to detect problems early and react before batch is finished. For post-acquisition data review, you want to do a holistic review. So you want to treat all your features, everything that you have collected, and all the sample types that you have, both for study and for QC. So in terms of batch failure, you could decide on what acceptance criteria you're going to use for pooled QCs. You can determine number of QCs that must fall within that acceptance criteria. And for sample outliers, you can use different approaches. For example, statistical outlier test. If you're running PCA, you can use Hoteling's ellipse to identify outliers. You can use internal standards, like in the example that I showed you. And there's another example here where you can see there is one sample where the extraction did not go well. So you know that this sample should be excluded. So finally, to recap key ideas. So in terms of design of analytical batch, our goals are we want to have stable system, we want to avoid bias, and we want to have sufficient QC samples to do all of our QC testing. For system stability, we want to decide whether the instrument is good to go. our pooled QC and internal standards are monitoring our technical variability throughout sample prep and instrument analysis. And then data quality review is looking at everything holistically and deciding accept, reject batch, accept, reject sample, and filter out and keep high quality data, and whatever is not good quality, get rid of it before you go for your biological interpretation. And as Victor mentioned, refining your practices over time is very important. You're not going to get it right on the first try, but over time, as you see different problems for your assays, you can definitely make it better. And also, as Victor mentioned, we are working on living guidance, so hopefully that paper is coming out before next conference, and it's going to cover topics beyond the 5 that I covered today. So thank you for your attention.
Thank you so much, Diana. And now, please, let's welcome Jennifer Kirwan. Thanks.
So, buenos dias a todos. That's all the Spanish you're going to hear from me. I'm going to be discussing GCMS best practices today. So, I always think it's good to know a little about your speaker. There are 2 things that are really important to know about me. The first is my amazing fashion sense. And the second is I work in Vienna, a land known for really good coffee. I'm the person who always insists on drinking tea. But I hear that you want to know about my GCMS experience. Thank you. Absolutely none. No, I'm lying, but it says something when Anna saw my name up there and she said, GC? You're talking about GC? Actually, I have worked in GCMS for the last 20 years. But it's a little bit secondary to our LCMS work now. And instead, I have to thank, if the clicker works.
I think it's a funny combination, because you have to use this one to...
I have to use this one?
Yes,
okay. I have to really say that I've learned most of what I know about GCMS quality control from this list of people here who were forming the GCMS group in mQACC, and in particular Oliver Fien, Ryland Giebelhaus, and Michael Herold, who have really been instrumental in pushing my knowledge forward. So, I think it's always good to ask, why do we need to focus on quality management? Ooh. I'm not making a very good job of the technical thing today, am I? The screen is over here, so I either have to look one way or the other. Okay, we want confidence that our data is robust, reproducible, and that results are biologically meaningful. Hopefully, if we get this right, it leads to increased time and cost efficiency in the lab. Ultimately, this means that we have better confidence in our planning and execution of experiments and reduced risk. Ideally, this also means we have better record keeping and assessment of progress over time. And believe me, record keeping, do it well, your lab becomes a dream. We get better staff engagement, better staff retention, and better onboarding. So it's well worth investing time and effort in this. Now, Dajana's just given us an excellent talk that does the basics of quality control, and she's concentrated on LCMS. She's done the hard work. I can go on to what's unique about GCMS. Now, I think 40% of you are doing GCMS. Can you put your hands up? Okay. So the rest of you can fall asleep? No, you can't. How many of you are thinking about doing GCMS? 1. Great. So I'm talking to you now. Okay. even if you're doing LCMS or any other form of MS or any other form of metabolomics, I think a lot of what we'll be discussing today actually often has a parallel in different types of analytical chemistry. So it's worth listening, I say. So GCMS, where are we starting from? Our metabolites have to be volatile or semi-volatile by definition. Otherwise, we don't detect them. And to make them volatile, we normally are looking at using derivatization methods. We're also using a different form of ionization to most LCMS systems. The majority of us are using electron ionization. A few people are also using chemical ionization. And we cannot do anything except start with the chemistry. And you'll see why when we go through this today. But please don't forget the basic lessons from LCMS. Okay, just because I thought that some of you may have never have done GCMS before, this is our basic GCMS workflow. It's not so dissimilar to LCMS. We start off with solvent extraction, and this often employs an acetonitrile step as well. Sometimes this is one stage, sometimes this is two stage, and we can commonly add internal standards at this stage. We then have to dry the sample. This is really, really important. Then we can think about derivatization. Again, this can be one or two-step derivatization before we do the analysis. And we can also add internal standards at the derivatization stage. So the first rule is that currently there are no defined internationally accepted best practices. I hope by the time I talk to you next year that may have changed. We're working on it at mQACC. Okay, it may be 2 years, but we're working on it. I'm always optimistic. However, there are some thoughts in the community about what is best practice. So I cannot talk about everything in the 3 hours I've been given today. It was 3 hours, wasn't it, Annie? But I do think it's worth mentioning the things that are particularly different about GCMS. I've mentioned the derivatization. The other point is to think about the temperatures at which you're working. We have particularly long run times compared to LCMS, and we're dealing with temperature gradients, not solvent gradients. And we'll get onto liners in a moment. So let's start with derivatization. Rule number 1, derivatization conditions will affect your results and stability. The results is clear, it's chemistry. The temperatures, the times, the pressures you're derivatizing at are going to affect your derivatization. The second thing with derivatization is that water affects most of our common derivatization chemicals and the derivatization efficiencies. And by water, I don't mean that you go to the milliQ and put in a liter of water. I mean the condensation that's formed when you take your samples out of the freezer, for example. Even really small amounts of water are going to have a massive effect on your derivatization. We can see this if we look at experiments over time. This is from Corewell et al. From 2016, I think it's 2014. And in this case, they did a series of experiments looking at different metabolites. And these particular set of results, we have multiple injections from one vial over time. So they took the same vial and made repeated injections. And what we see is that it has no effect on some metabolites like glucose and fumarate, but with metabolites like GABA and glutamine, we're seeing a massive drop-off in intensity and detection over time. When we look at the same experiment, but now the same sample is divided into multiple vials and is injected one injection from each vial, We largely lose this effect, at least for GABA, although we see for glutamine that even after 24 hours, we've got a 50% loss. Now, what's the difference? Well, Corewell et al. At least postulated that they think that this multiple injections from the same vial was letting small amounts of water into the vial. And those small amounts of water was enough to catastrophically reduce the detection rate of your GABA TMS signal. Glutamate is obviously, glutamine and glutamate are obviously less stable anyway, and therefore our only recourse is to make sure that we're actually not derivatizing too many samples at a time. We need to talk about internal standards. Internal standards have very similar roles to LCMS, but now we have this extra complication of derivatization as well as sample extraction and technical considerations. So we have 3 types of internal standard that are commonly used. One are standards that are not derivatized. And examples of these are alkanes and fatty acid methyl esters. You can derivatize fatty acid methyl esters, but in this case, we're often using them as non-derivatized internal standards that we can assess the technical reproducibility of our GCMS. Then we have standards that we're putting in because they are derivatized, and that allows us to affect to measure the efficiency and the stability of our derivatization products. And these are things like norvaline, cinnamic acid, anything that you can think of that is not in your sample. And an increasingly common thing to do, although it's very expensive, is to use deuterated derivatized agents. So these are now heavy labeled agents to construct a twin metabolite. And this more specifically follows your metabolites of interest and how they are responding to derivatization and individual extraction, derivatization, and analysis conditions. We think a lot about derivatization conditions, but temperatures after derivatization also matter. And again, we go back to this paper by Corewell et al., where they show that the temperature after derivatization also affects your stability, particularly for glutamine and glutamate. Basic rule of thumb, once you've derivatized, try and store at a lower temperature. And if your instrument breaks down and you want to save your samples, then think about freezing. If you're thinking about freezing, think about water and condensate at the same time. And one of the recent technological advances in the last 10 years has been online derivatization. How many of you are using online derivatization? Only a couple, okay. This looks expensive technology to buy, but it has massive advantages to implement in your lab because it reduces your variability for individual metabolites over time. So you save money on the bioinformatics afterwards. It enables longer batches, and it reduces your batch effects. So if you set it up carefully, it's really, really good. But it is expensive to install and set up and maintain. And if it's not available to you, it's not the end of the world. Most of my GCMS work has not been done with online derivatization. You just need to think about your batch length. So I'd advise not keeping samples for more than 24 hours if they've been derivatized. And you need to be monitoring those derivatization effects with QCs from unique vials. And don't forget your bioinformatics at the end. We carefully check our QCs and our drifts and exclude metabolites where the variability is too high. Now we get onto inlet conditions, and inlet conditions I could spend a whole hour on, but I'm going to concentrate on liner choice. I think there are something like 100 different types of liner out there, and this is totally overwhelming when you first start. it's good to think about the basic physics of liners and why we use them and how you want them to work. So liners come in different sizes, in different shapes, with baffles, with glass wool. What you want to think about is the geometry, your packing material, and your deactivation. So basic rules of thumb, if you're doing split injections, you need to think about making sure that your sample is having time to thoroughly homogenize and be representative before it's split. If it's splitless, then you want to make sure that you're not allowing non-volatile compounds into your system, because that's going to affect your analysis. So we tend to recommend something with a large surface area for both, so that you get maximum heat exchange, so that the sample is evenly heated and able to go fully homogenized into your system. And this is where baffled liners increase sample mixing and surface area and really help. I always used to use glass wool, but recent advice, by recent I mean probably the last 10 years, is increasingly showing that glass wool has lots of catalytically active sites and is probably best avoided unless you're interested only in certain metabolites. The volume of your liner is crucial, because if it's too small, you get poor reproducibility and contamination, which leads to peak tailing. And if it's too large, you get increased dead volume and uneven heating and peak tailing. So either way, it's not good. And you really need to think about your vaporization volumes. For reasons I don't truly understand, they always give pure solvents, but things like MSTFA, which we use, are never really considered. I would say this is where your technical helpline of your GCMS liner provider is really helpful. They can often advise the best liner for the job. This is the consequence of not using the best liner. This is from Thermo, and we see exactly the same sample. Unfortunately, they haven't given us the conditions, but you see you get the right liner, you get beautifully shaped peaks. You get the wrong liner, you get rubbish. And make sure your system is stable before you start. You cannot avoid spending time maintaining your instrument or spending money on consumables. The brutal truth is that mass spectrometry is expensive, and everybody's laughing here. And if you want to do it well, you need to have the budget to change liners regularly, change seals regularly, and monitor regularly. Run conditioning samples in exactly the same way as LCMS, but you have to take account of the longer run times, and also think about blanks to avoid carryover and to assess it as well. And just like in LCMS, QC samples really help you to measure your technical variability. So I'd like to draw your attention to the closest thing we have to best practices, and this is this paper, which was a survey of best practices done by the GCMS mQACC working group. And there's a QR code, but also it's on the list that Victor showed earlier. And this mentions volatiles. So I'm going to quickly move on to volatiles to say, if you're interested in running volatiles, go and ask someone else for advice. It's incredibly complicated to try and standardize this, and I cannot cover it today. Otherwise, I've left some interesting references at the end here. The slides will be available to share. And Annie is waving at me to say, stop talking. So I will hand over to Leo, who's going to talk about NMR.
Thank you so much, Jennifer. So now please, let's welcome Leo Cheng, who's going to cover NMR today.
Sure, let me change gear today now here. We heard from my colleagues about LC and GC mass. To me, it sounds very complicated, very difficult to do, a lot of steps. For NMR, what I want you guys to take home is this. With NMR, as long as we do certain QC, what I'm going to talk about, the result is reproducive. We don't have this kind of curve. You see, Jennifer just showed it would each shot will be different. We won't have that. We're reproducible. We very cheap. There's almost no cost other than you buy the NMR instrument. And yes. So, but what I'm going to show you is my slide is a kind of very crowded. Don't worry about it. We will go through very quickly. So the first, because I saw the survey, we only have about 10% people doing NMR. So we talk a little bit about NMR so you will appreciate what I just said. So the first thing is you want to pay attention here. Certain nuclei which has NMR effect. Fortunately, all the biological sample has certain isotope which can be measured by NMR. So that's a very good thing. The second thing I want to show you, want to pay attention here is NMR is very specific in terms of what chemical group we're measuring, as long as you measure correctly. And then we are not very sensitive in terms of measuring the amount, because the signal to noise, what we talk about, is kind of low. The reason is the distribution we are measuring, the difference is very small, so we measure the difference. So that is the disadvantage of NMR. So a lot of time we have to do signal average in order to increase signal to noise, okay? So that is the most important part here. And then there's a lot of things which affect this number. This delta E is what we measure. This number actually relates to a lot of things, which including the chemical environment. And then you can think about pH, temperature, they all change. So that's the QC part that I'm going to talk about. The good thing, what we are talking about here is with NMR, we don't need to do sample preparation. Just put the raw sample in, you measure it. And that's not completely true. If we measure urine, then we do need to do something there because pH is different. pH is different. You have to you move the pH to titrate it to 7 in order to get a good result. So with urine. But with blood, we don't need to do anything. We just put the serum or plasma into NMR tube, we do the measurement, that's it. But you will see, if we look at the whole spectrum, you see a lot of proteins there and the micromolecules. So that covers a lot of small molecule which you don't see it. But we have different way to measure it. As long as each time you measure the same way, it's comparable. So we can do that. So in reality, what we do is here, we have the sample here, and then we put into right now we have different NMR tube. The important thing is, right now we have this 1.7 millimeter NMR tube, which Bruker has it. And then we only need to use, this actually, my colleague put this wrong. This is not 60 microliter. We're talking about 40 microliter, 30 microliter. That's all we need. And the important thing with NMR is we do not destroy the sample. So after you measure NMR, you can measure mass spec if you wish on the same sample. You can do that, okay? But mass spec, you cannot do mass spec and then do NMR, right? So I'm doing salesman. And then you can see with different part, you can see this is the we call upfield. Okay, this is downfield. This is upfield, and then we can see there's different metabolites and different metabolites here with urine sample. You can actually see all those. And now we get into the quality control part. The important thing is with NMR, the most important thing is we need to have a homogeneous field in order to get a good spectrum. So that is, if there's not homogeneous, you got a spectrum something like this. If the same sample with homogeneous field, you see all the different peaks. And the way to get homogeneous in the NMR field, we call it shimming. What is shimming? Shimming is in the old time when people make shoes, and then they have to put a small chip, a wooden chip, to put in between the two big blocks in order to make the size. That's called shimming. And we're using electronic current to make the field very homogeneous. So that's called shimming. So with NMR, the first thing is you need to have a good shimming. That's a homogeneous field, okay? And MRI is different when we'll talk next time. So that's the shimming. And then with the good shimming, and then you can see with different sample, we can get different spectrum, very high resolution spectrum. And these are reproducible as long as you have this shimming controlled as well. Now we're looking into different QC part. That's what the important part. So the first thing is, because we are measuring radio frequency sample from the sample, okay? So this is almost like what you listen to the radio. The old time, now probably all the diodes. The old time, there are two knobs. One is basically the volume. You turn the volume. The other one is you turn the station. And that is the tuning we're talking about. You tune the station and you tune the volume in order to hear the radio. That's the same thing. That's we call the receiver gain. That's the volume. You turn the volume. You want to turn the volume up, but not too high. If you turn too high, your ear couldn't take it, right? So you cannot be too low. Too low, you don't hear. Too high, it's not good. So you have to get the right receiver gain correct. And then we're also talking about relaxation. You have to measure the relaxation correctly. Relaxation is like what? If you have two magnets, and then they will stuck into together, right? That's all the experience. And then if you turn one like this, and then if you release it, it will go like back to here. This time is the relaxation. You relax back to there. And with NMR, because we said NMR is not very sensitive, we have to measure multiple average in order to get a good signal to noise. So you wanted to get completely relaxed back, and then you measure again. So that's relaxation, and then we have to make sure we give enough time for them to relax. And also, because we talk about the number of scans, because we say the signal to noise is not very good, so we have to get enough scan. So you can have, if you have too much, you have just one scan, you probably don't see signal. So the signal to noise is bad. And then you have like 8, maybe you see good enough. And you have, if you do 64, maybe too much, you waste time. So you have to get a good, right signal to noise time. And then also, this is we're talking about the relaxation is just like the two magnets trying to stick together. So that's relaxation you have to consider. And then also the temperature. Because the temperature change, you actually change the chemical environment. So it's very sensitive for the nuclear to fill. So you have to keep the good temperature, and also the pH, I think we're not listed here, but pH is the important part too. Now, this is the beautiful part we're talking about NMR, because whatever the peak you measure, as long as you keep my QC procedure each time you keep the QC procedure, the peak intensity you measure is directly related to the concentration. You can do the conversion immediately. And then normally what we do is we use the internal standard. We know the internal standard, we know the amount, the concentration, and with this formula, we can do immediately, we can measure the concentration of the metabolites. So that's how simple it is. So why don't not many people doing it? It's simple. It's simple. And then we just mentioned about the internal standard. Internal standard is you put a chemical in. You put a chemical in your solution. In your solution, you measure it at the same time. That is the most sensitive way. The reason is because if you use an external standard, which you have the sample here and then you have the standard here, you put it in the middle, that is something which you can think about. There's a glass, there's a sample, there's a glass, there's another sample. When you change from one material to the other material, you actually reduce the homogeneous of the field. So the nuclear feels differently when you change this way. We call it susceptibility. You break the susceptibility. So that's not very good in a way, but this is the way most people are using it. The reason is if you put an internal standard there, sometimes it reacts with your sample. For example, normally we call the DSS, we call the TMS. Most time we're measuring the internal standard. If you put to measure blood, it will react with protein, and then you won't be able to see it. So that we have to choose different standard. We do have different standard which can be used, but you have to be careful. There's no interaction, chemical interaction happening, and then there's also some kind of artificial generation of the standard. There's the outside, which is not very good from my point of view because they are not in the same environment as the sample you are measuring. Okay, so these are, and then the next thing is we can also do the randomization if we want to, because currently we have 96 well, and you can randomly pick up. A Bruker is just a fingertip. You can pick up any order you want to run, and then you can run that too. You can run the standard, you can run the pooled standard, everything you can do that. So that is the current technology. Now let's get into the this is the QA part. The QA part basically, we made this slides, which is very condensed. It's best for your homework. When you get after this, you go home and then read. I'm not going to read this, right? So basically, for the QA, is you document everything. You need to document everything. You need to have the SOP. You need to have the repository. Everything you need to do. But the important thing is you need to generally have a good practice procedure, and then for each step, you make sure that the data is all backed up, everything is according to the SOP, and then you continuously improve. Now, very last one, very last one. This is the same sample, the same set of sample. If you have a good QC, as I say, the shimming is good, everything according to the QC procedure, and then you can see if you do maybe this is a principal component analysis, you see the difference between the two groups. And then if it's the same sample size, if the QC is not good, you basically everywhere, and then this is one is a good with a good QC, without good QC, and you can see this is the distribution of the PC, and then this is basically mixed everything. So the QC is very important. I'm done. All right? Okay. Yeah.
Okay, so please join me in thanking Leo, and let's welcome Mariana, who's going to cover reporting good and best practices.
Hello, everyone. Good afternoon. So over the presentations we had here today, we learned about practical quality controls approaches across LCMS, GCMS, and NMR, which is very cheap. But there is one final challenge, because even when quality control is done properly, it's often not reported in a way that allow the readers or even future users of that data to assess analytical quality or even to replicate experiments. So I'm going to focus the last 10 minutes on how we communicate quality controls to others. I think we all here agree that we spend considerable effort into QA and QC in our labs. And this will give us an increased probability of reproducible results and provide us with documented robustness of experimental procedures, allowing us to calculate technical error in our data. And all this will help us to understand the quality of the data. When the QA and QC is reported properly, the results can also be properly interpreted, and they can be replicated, meaning that the world will understand the quality of the data. So what we want is to move from that hidden, well-kept in the lab QA and QC towards transparency. So how do we make QA and QC visible in publications? The presentation that I'm showing today is based in this publication. I have only 10 minutes. Annie is controlling me very well. She's very mean. Please refer to this publication if. Please refer, I'm kidding, she's very nice, right? Please refer to this publication if you want more in-depth information and more details regarding minimal requirements and best practices in reporting. But here you see that we recommend reporting to be structured around 5 pillars that will cover the entire metabolomics workflow. So just going a bit more in depth into each one of these pillars, the first one is materials, and as minimum practice, we should be reporting the identification of the quality controls, and this would entail, for example, type and scope. So, for example, we should detail if it's an in-house QC or a blank sample, and also if they were used for within batch or between batch precision. But also it's very important to note any other materials that were critical for data quality, such as a column, rages, and calibrants. When moving to instrumentation, it's important to detail the type, vendor, and performance characteristics. And in sample handling, it's important to detail how the sampling was done, the samples were stored, and how they were prepared. And moving to analysis, it's very important to detail all the information needed to replicate that analysis or that experiment. So that will include all the method, protocols, details, and the analytical system settings, which for mass spec will include the chromatography parameters and the mass spec parameters, while for NMR that would include, for example, the NMR experiment details and the pulses. It's also very important to include the analytical sequence description, which will include the sample run order and the QC frequency. Moving on to post-analysis procedure, it's also very important to list and explain how the data processing was done, and that will include the software packages that were used and the settings. And that will explain, for example, how the extraction parameter settings that were used, how the data was filtered, and how the data was normalized. But also, very importantly, for the QC data analysis, we should be listing the statistical methods applied, the acceptance criteria, and the control limits. Very importantly, and I also want to say that's not the scope of today's talk to go more in-depth into confidence levels, but it's paramount that we understand the differences between annotation and identification. And as summarized here in this table, identification will require matching 2 or more orthogonal data types that are compared directly to in-house standards that were evaluated under identical experimental conditions. This will provide with a higher level of confidence, and it will be, for example, when you're comparing your MSMS and retention time, and you're matching it to your in-house libraries of standards. In contrary, in annotation, it generally involves 1 or more orthogonal data types. There is no comparison to authentic chemical standards because the data is evaluated against or compared against public external repositories. This will provide a lower level of confidence, and an example would be when you have your MS or your SMS matching to public databases. The key home take message here is not to avoid annotations. Annotations are pretty much fine, but we just need to be transparent on the level of confidence of each metabolite reported in our publications. I've also added a QR code here for publication where you can find a more in-depth explanation between the identification and annotation and how is the best way to report the confidence levels. Going back to the first publication that I mentioned by mQACC, when we are talking about quality control samples and the reporting, we need to be very transparent about every single quality control sample that we included in our study. And those can be for all those samples listed that were already explained in the previous talks. And we recommend some minimum requirements for each one of the samples used. Those will include intended purpose, if they were used in the study, the category, technical description, the quantity, and if they were analyzed per batch. And here in the publication, you'll find a template for this reporting. Thank you. And the idea is that instead of writing a piece of QC different for each publication, each manuscript, you have a defined structure that's easier to fill and easier to read for the readers to understand the data and also to compare across the studies. So just having a visual idea of how this would look, so we would have a table like this. So this table can be much longer because you can have not only the minimum requirements, but also the best practices. And for each one of the samples included, you're going to describe very well how they were prepared, how they were used, and if there are any other, if there are any extra method details about those samples. With this, for example, we can learn how the contamination of background noise were controlled in this study, but it will be this multiplied by all the other quality control samples that you have included. Just to wrap up with some examples of things that we are trying to avoid, and I think examples we all see in the literature. I put 3 examples here. The first one is like the authors mention the internal standards, but they don't say what they are, the concentrations, what they were used for. A second example in which some details of the chromatography is listed, but there is no gradient, so this is impossible to be replicated. And the third study in which the only thing we know about the processing is that peak identification was performed with XCMS, so we don't have how to access the rigor of annotation, identification, selection criteria, and so on. And just to end on a good note, for the quality control samples, what will be a good reporting is that when you list the samples that were used as a quality control, how they were prepared, what they were used for, they were injected multiple times through the analysis. Again, they were used for signal drift correction. And then again, we have another type of quality control sample, which are the blanks. Sample order was randomized. So with all that, it's much easier for us to assess the analytical quality of the study and to understand how any potential limitations that might have occurred. And just to wrap everything up, the key takeaways on reporting are that reporting standardized metrics ensures data transparency and is the final layer of quality control. So I think it should be all in our mindsets, or we should include reporting in our quality control workflows in our labs. And we recommended a framework to stay globally aligned. And as a community, we should normalize reporting QC metrics in every publication. And I'm adding here some final acknowledgements for all the team. And I will just skip to the last slide so you can find us through this QR code. Thank you.
Thank you very much, Mariana. So now I think it's time for some discussion. So if you have any questions or curiosities or points you would like to discuss, Julia will be leading the discussion now.
Okay, so yeah, thank you everyone for sticking around. I think my colleagues made a fantastic job in walking us through the main technologies that we use nowadays for metabolomic studies, and also on the last part on reporting. Actually, when we performed the literature surveys, we noticed that a big part of our of the problems or the challenges that we face are related to the reporting, right? So poor reporting is really something that I think we will have to work on in the future, like to improve this poor reporting, of course. So now the floor is open for your questions and for discussion. So, yeah, are there already some questions, please?
Yeah, thanks. And that's the perfect opening for my question because it's exactly on data reporting. I would just share my perspective so maybe we can start the discussion. Because I see two main points that you obviously did a tremendous job in getting the people raising the awareness. So you see people are using QCs and internal standards and so on. But yeah, the reporting, it's still limiting. So my first point is, for example, for the template that Mariana showed, I don't know, I think we should maybe push it a bit more in the sense, for example, I don't know, that the Metabolomics journal, it's kind of maybe even mandatory that people have to upload that template field so that everyone can get a grasp on the basics of the QCs of, I don't know if it really,
yes, so
it's good for every single study, but yeah.
Yes, I'm so excited. Thank you, Vinicius, for that question. And I must underline that we did not plant this question in the audience. So actually, the Metabolomics Journal does already use this template, and all the authors are encouraged to submit this table that is a supplementary table of the paper, to submit it as an...
Encourage. That's
yeah, so... Well, you know, we do not want to be too strict about things because sometimes then you just achieve the opposite, right? Today it's a recommended. I see Jennifer wants to comment on that.
Okay. I think that we need to be clear that we as a community, as an mQACC community, can only persuade. We cannot enforce. But what we are doing as an mQACC community is we're engaging with editors and publishers because they are able to enforce. And the feedback that we've had from several publishers, including Metabolomics, and a big shout out because I've been very supportive of this, is that the editors are actually extremely supportive. They also require you as the peer reviewers. First of all, please do take on peer review. It's very difficult to find peer reviewers these days. But they also require you as peer reviewers to actually follow their recommendations that says, have these templates been filled in, you know, tick box. And we have designed it deliberately to be as easy as possible. So the templates are designed to be software non-specific, very easy to use. And although it takes a little bit of time to set it up the first time, once you've done it as a lab, it's a 5-minute job with every experiment just to fill it in and add it as a supplementary. So we need to be working together as a community. So go and talk to your local friendly editor. If you're doing a peer review, ask where the QC reporting standards are, and try and publish in journals that are supporting such initiatives.
Thank you.
Yeah, so maybe to expand a little bit on that, you mentioned Metabolomics specifically because it's the Society's journal, and many studies are published there, but also many other metabolomics studies are published in other journals, right? So we are also reaching out to many other journals, and we try to really, spread the word broadly to get reinforcement on that. And we, as mQACC itself, as a group of scientists, we do not want to be prescriptive, and we also are aware that, different studies have a different scale and a different scope, and it's not so easy to define something that can be universally applied to everything, right? So it needs to be somehow, also easy to complete it, and but we still think that it's a useful tool, and it will help us to do the next step forward in the right direction.
Can I follow up, or? Okay, I'll give the floor to other people, then I...
Okay, thank you.
Okay. No, and then the second point is that I think it's also still lacking a bit for the reporting that I see in many papers, also as a reviewer, is annotation, because the very basics, even from getting the same metabolite annotated 3 times on 3 different retention times, or not even putting the annotation confidence level, I don't know exactly how, but from my perspective, this is also a key point that we need to work on, because all the biological discussions are based on that, and if that's wrong, everything else is wrong. So thank you.
Yeah, I mean, that's the known bottleneck of LCMS metabolomics, right? Maybe we can, in other techniques, it's not such a big issue, right, Leo? Or, yeah, GC. So it's cheap and easy. Of course, that's true, and the reporting is particularly important for that stage, I would say. Yeah.
Can I? Okay. Well, first of all, thank you for the presentations. It was very, very interesting. I work in computational metabolomics, LCMS data processing, and sometimes when we talk about QA/QC, we kind of focus too much on the instrument variability and sample prep and this kind of more analytical side, and I have seen that on the computational side, there are also big challenges from the fact of choosing which software we're gonna use for data processing to the level of optimizing the parameters for the software. And we have seen, which is quite surprising, and I know everyone has seen this, is the fact that we run the same sample set in different software, we get different results, the overlap of features detected by different software is different. We don't know really if the processing parameters we're choosing are correct. And basically my question is, I haven't seen this initiative. It's really nice to know that you're working on that, on this direction, but do you also consider the computational side in the QA/QC?
Yes, and if you want to get involved, come and see me afterwards.
Perfect.
Yeah. Okay. Yeah. I think that's a very important question you are raising. Also, because maybe here the diversity even is bigger than when it comes down to the analytical methods, right? Because I think every lab has its own workflow. You can combine different software packages, and yeah. So that's really. Maybe that's something that we will take up also, as you said, in the future. We did not really talk too much about that yet.
We have a working group in reporting standards on just this issue.
Reporting standards, but yeah, they have to, expand to that part of the...
And best practices also, I think, probably it's a good area to go into.
Yeah, so we focused now more on the pre-analytical and analytical part, and on this side of the workflow. But of course, the work is not done once you obtain or pre-treat your data.
Hello?
Yeah, hi.
That works. Thank you very much to all of you for all the contributions. All of them were very convenient, starting from the presentation and the organization, for example, the description of the batch, the all one single batch and the multiple batches, and also the reporting guides and recommendations, and GC. My question is for Jennifer about GC. I guess that we started with GCMS more or less at the same time because I have been working with the instrument more than 20 years. But I would like to add that the influence of water depends on the kind of reagent or the derivatization reagent. And perhaps for simulation, of course, water influences a lot, but glutamate and glutamine are the worst analyzed to be analyzed with this reagent and with that technique. Do not try. But there are other choices, for example, based on alkylation with chloroformates that were perfect. Water or the humidity is not a problem. That's all.
So I entirely agree, and we didn't even go into the issue that glutamine and glutamate can transfer, can convert into each other in the GCMS. Point taken.
And finally, also, I would like to add the question of internal standard and the selection of internal standard is even worse with different kind of specimen, for example, exhalates of breath or whatever. That is another story for another meeting. Thank you.
Hello, everyone. Thank you. That was a very nice session. So on the template you have for reporting, I want to ask if there's also a template before you start doing anything. And I'm asking this for people who are newer in the field. We have a lot of clients, and I got an email this morning from a client saying, I have 4 samples, can you do metabolomics for me? So if there's a sort of template that we can give someone to start off with. And the second question is, have you looked at sample stability as a group? Because I see too many times that people use 20 or 40, 50-year-old biobank samples to do metabolomics, and maybe then collect controls now on campus, and then you can't really compare those. So sample stability, but not long-term sample stability.
Diana, you want to answer that, maybe?
Okay, so I can answer on the sample stability. mQACC as a group hasn't looked at sample stability. There's been different publications across from different groups. On that, it's a very important part and very overlooked part. And my advice on that is, right, you can also double check your stability for your assays, your extraction preparation. So as a group, mQACC is not working on it, but it is a very important part of ensuring good quality data. And there is some good publications looking over the years, but, and in terms of template for a pre-design of the study, we have not focused on that at all.
I was going to mention what Jennifer just mentioned, the BP for NTA. I think you are in contact with them, right?
Yes.
Yes. So maybe for you to know, there's the BP for NTA group, the best practice for non-targeted analysis, more for the environmental focus, but they do have a study reporting tool, which is similar to the template that Mariana has showed. And I believe until the end of the year, the study planning tool will be published. We are working on the paper now, so it's going to be something that for sure can be used also for metabolomics. Yeah.
Yeah, thank you so much. My question is for Diana LCMS. In the end, you kind of showed the QC that can be used for like metrics effect, and you show like the dilution. So I was just kind of like asking if you can elaborate more, because in there, is that they should be at the end or should be at the beginning, and how is that analysis related to the matrix effect. Yes, and then just a quick comment on the sample stability, because we've got a cohort that has been 2016, so we will a long time. And then also metabolites have changed, and there's oxidation, there's so many things happening. And then if I analyze the sample, even a cell sample, I do the extraction today and I keep them in the freezer. The next time I'm looking at them, they've got a different profile. But how do you follow that? So even the people that are coming up with the recommendations and the strict rules, they should also consider how this metabolite changes over time, that we cannot have the possibility for that.
Oops. To answer your question about the QCs that are used for linearity and matrix effect, so what you are doing there is you are building correlation coefficient across metabolite with dilution. So if you see that you don't have a high correlation between your dilution factor and the signal, then it's telling you either you have something like detector saturation, very severe matrix effect, so the signal is not scaling properly, or maybe you are misidentifying some extraneous signal that's coming somewhere from system and thinking it's metabolite, and then when you dilute it out, it's not following the trend. So it's done by correlation analysis. And in terms of the timing of the sequence, I don't know, in my lab we usually do it at the end. I don't think it matters where you place it in the sequence, but if you're worried a little bit about column deconditioning, and that goes back to the story of the blanks, that's why we like to run it towards the end. So if it does decondition the system, after that you are not running any more study samples.
Okay.
Yeah, and Matt Lewis has some nice publications as well, so yeah.
Thank you so much for all your presentations. I think this topic is really important. And this might be, I don't know, for you guys maybe an obvious question to answer, but we work mainly with thermal instruments, and we've noticed that we don't really have a system suitability testing approach established in our lab yet, and I think that other vendors can easily track all of these data and then over a longer period of time, but Thermo does not, to my knowledge. And I wanted to know if you have like any recommendations for working with these instruments, or do you then track it like manually in your lab books and then do this? Yeah.
So, I don't know, Jennifer, you were working with thermal instruments, I think.
Yes, and come and see me afterwards, and I'd be happy to discuss this with you. But in general, what we do, we find most vendors have very simple system suitability tests, and they're often more designed for proteomics rather than for metabolomics. So what we've done is we've basically bulk bought a load of cheap plasma, and then we monitor certain metabolites within that plasma, and we track it somewhere centrally so that we have a good idea what it's doing.
But you do it manually?
Shall we say we do it semi-automatically?
Okay.
I think that the software you use is not that important for this purpose. You can set this up, I'm sure, in a different way.
Yeah, my lab even just has a simple Excel sheet where you record certain parameters like retention time of several analytes or peak area or things like that. So even an Excel sheet, but that you religiously fill out every time you run can help.
A nice thing about a biological sample for that too is you can find low level. A nice thing about a biological sample for that SST is you can also look for metabolites that are near limit of detection. So you can see, is your instrument as sensitive today as it was yesterday, right? So actually looking at peak detection. So finding some low-level metabolites that are right on that edge. And that way you can say, is my instrument as sensitivity? Because, we can't always trust the area or, so having that, did I actually detect the peak today, can be really helpful. And that's, I find, at least best from a biological, because then you have lots of options to track.
And also, I'm not able to recall the details, but I remember that a few years ago there was some application note or something like that by the team working on Skyline. and they were describing how to use their software to automatize keeping this record of how some SST was behaving over time. So maybe if you do a quick research on the internet, you can get the...
I'd also say if you're doing metabolomics, then having a complex SST, having a simple instrument vendor, one peak SST is better than nothing, but there's a real benefit to having a more complex SST.
So, any other questions? I think we still have some time. Any? 6 minutes, okay. We still call it coffee break, even if people have tea.
My question was on the use of the QC sample for normalization. How is the status right now? Because in the past, there used to be, you have to use protein, you have to use DNA, anything of that. But how is the situation right now? Can we go ahead and use the QC sample for normalization, especially when there's so much now bioinformatics website that are kind of incorporating that into normalizing the intensity and then putting everything together? So what's the status?
So you mean to compare between different batches or
within the batch,
one batch?
Within one batch, then you use those QC sample like what was shown there, and then because you have the QC in the beginning and you have the QC at the end, the intensity, there's a drift in there, so you use the intensity brought to the same level, and then that normalization, you can now do the statistical analysis on the sample that has been normalized with the QC sample.
Yeah, so there are different methods to do that, right? And but I would not just call it a simple normalization. It's kind of a correction, right?
Yeah,
because
exactly.
you would correct each variable separately.
But then you're not using protein, you're not using DNA as part of the normalization, you're just using that, no?
There are two different types of...
Yeah. Exactly, that's why.
Because when you see you correct the analytical drift and analytical variation with proteins or, sorry.
Yeah, please, go
with proteins or, I don't know, with creatinine content for urine, you corrected the biological variability between the samples. So they are completely two distinct things. You can merge both of them together if needed. But with both methods, you are addressing completely different aspects. Like one is purely analytical, and another is, I would call it biological.
Biological.
I'm going to say for those of you who are confused by this discussion, I think we're talking about cells in particular, and creatinine. I would say our experiences don't use creatinine, use specific gravity. But here is a really important thing. You're talking about bioinformatics normalization. It's too late. The mass spectrometer will behave differently with different massive differences in concentrations. You want to have pre-analytically corrected for things like differences in urine concentration or massive differences in cell protein. The cell protein's difficult because it depends why the protein concentrations are different. But if you've got very different cell concentrations, try and correct that pre-analytically. Don't rely on the bioinformatics.
Because the reason is that it may affect the sensitivity of the different metabolites, right? So.
And also, you're looking at the data metrics in two different directions, which are orthogonal to each other. So when you talk about how to use QCs to track the drift of one particular variable across the samples, then you're doing it one variable at a time, and you're doing it over all of the samples. While when you are looking at any resource to normalize your samples, you're doing it for all of the variables in one particular sample at a time. And this is when you're using either specific gravity or protein concentration or total useful signal or PQN, you name it. So you usually combine both processes to first to normalize the original amount of biomass which was available in your samples, and also at the same time to take into account this analytical drift which is happening over your analytical sequence.
So we have time for one last question, I see. if there are none, then I think we can close the session. I would like to thank again. Oh.
Where do we get the best cup of tea around here?
Well, I don't know. I have to pass on this question. Okay, thank you very much for attending.